should. Okay, so last time we talked about some advanced features of SQL queries. We talked about SQL, we talked about from clause, where clause, and all of those things. We also talked about group by, order by, and basically aggregate and your grouping operations and things like that. One thing that you need to remember in SQL is that in general, unless you set up your database otherwise, in general, SQL and as is your relational algebra operations are case insensitive. So when you say select, and this is just a standalone statement that does not include any databases, and you can actually run this code. So select in within single quotes capital hello equals to within single quotes small hello. This would actually evaluate to true, right? Because they don't have any case checking. This sometimes can give you some weird results when you're actually working with grouping and aggregation type stuff. So for example, let's say that we have a database called favorite colors. We have a table called favorite colors that basically lists the name of the person as a primary key and the favorite color of that particular person, right? So let's say that we add data to our particular table. We say insert into favorite colors values. And let's say Alice really likes blue. So she shouts out blue, all caps. And let's say Clara sort of likes blue. She says blue. And we have Bob that says red, right? So let's say that I want to know how many people like each color. Well, for that, we can say select color, count star, num people, from favorite colors group by color, right? And for that particular scenario, we know that since SQL is case insensitive, both blue and this lowercase blue would be grouped into one particular count statement. And essentially, we would, since we are grouping by color, both of this and this would by default be grouped into a single thing. And we say that two people like blue, right? So blue would have two, red would have one. But sometimes this basically becomes a bit weird because what would be the resultant values of your table, right? Would color be all caps? Would color be all lower cases? What is the resultant color of your count star of 2? So in general, it is a very good idea to normalize your values when you insert values in your data. So in general, it is a good idea to always say that all of my data in my table will always be in lower cases. I don't care about upper cases, it should always be in lower cases. So that is where you have your pre-processing of your data before you enter something in your database. That also makes it easier to evaluate something or visualize something when you're actually looking at the database itself. Now, when we are comparing things, we should always mention that yes, comparing different cases does not matter. But again, comparing null values result in different things in different cases, right? So like in relational algebra, SQL also, like in relational algebra, SQL also allows you null values and the comparison operations are also similar. So when I say an attribute is equals to null, even if that particular attribute is null, it would still return as unknown. Remember, unknown was our third sort of Boolean type that we cannot compare anything to null. So that resulted in unknown. So is attribute equals to null? Even if that attribute is null, it would return unknown because how would you know if it is null? Null is an unknown concept. Same applies to attribute not equals to null. Again, it's never true because again, we can't compare if something is or not null. So 13 not equals to null would also result in unknown. In general, we would want to work with as few null values as possible and ignore null values if there is the possibility. And also remember that null behaves differently in different cases. So if we have count as our aggregate operation, it would return 0 if I have an empty multiset or a group of values that are all null. Count would return a 0. However, other aggregate operations, sum, min, max, those would return a null or an unknown value, right? Because they don't make any sense in terms of adding up null values. However, count actually returns a zero. In general, you can check for null by checking if a particular comparison is unknown or is not unknown. For all my life, and I have been working with databases for quite a while, I have never had to use unknown or is not unknown. So if you work somewhere that actually works with null values, I mean, that is a very poorly designed database that you should actually avoid. And if you do in your work life actually get to a position where you're checking for unknown values, do let me know why. Because essentially I've never seen someone use unknown in the first place. But yeah, it's just a thing that you can do. Okay. We can actually specify that we want to insert a particular null value in our table. So we can say insert into account values A315 null 500. So this means that we are trying to insert this tuple into our account table, and the account number is A3115, and we are saying that we don't know the branch name. So our branch name here is null. That is usually never the case, but however, you will be able to play around with some null values in this particular assignment that we have. We can also have other null values. For example, our balance can be a null value. Again, why would you want to have an account in a branch that can allow null values, right? So again, usually not the case, and it would clearly lead to some problems because again, different aggregate operations work differently. Comparison operators don't work with null values, and it's an entire mess, right? So we would like to have certain checks on the tuples that we can allow, and we don't want to have null values at all. One way to actually restrict null values is that if we have a primary key, usually, I mean, in general, primary key attributes are never allowed to have null values. If you remember, our account ID was A3115 and your account ID is blah blah blah, they can never be null. However, if we have attributes that are not primary keys, we can actually allow null values, and there are ways where we can say that this particular attribute does not allow null values, and we will talk about that later. And essentially, we will talk about check constraints and whatever things, and this comes up in homework 4 or something. So we'll cover that later. Okay, so up to last class, we talked about our join operations. We talked about our Cartesian product operations that we had. We said that if we had used the from clause, that was essentially a Cartesian product. So we can have multiple tables using the from R1, R2, R3, R4, and that all of those became your Cartesian product of tables. But SQL 92 and onwards actually introduces a new set of joins that we already know about. That is your natural joins, your left outer, full outer joins, and something called a theta join that we will talk about in a second. But essentially, all of these joins, if you remember correctly, can actually be achieved using a Cartesian product and some predicate on that Cartesian product, right? Where blah, 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 where borrower.loan ID equals to loan.loan ID, that got us a natural inner join. But SQL 92 standards onwards also allows us to specify a particular join to make our life easier. So essentially, these are all syntactic sugars added to your code. And most of the time, I definitely almost always use these things. So natural joins, left outer joins are basically going to be your bread and butter for this thing. And also the homework would also require that you work on these as well. One thing that we did not talk about when we talked about joins in relational algebra is something called a theta join. So if I remember correctly, our natural join was an equality operation on a Cartesian product, right? So our Cartesian product, we equate all the common attribute names, and then we get a resultant relation. A theta join is a generalized join operation which in relational algebra looks something like this. We have R, bow tie, and a theta, and then an S. So that is what we represent a theta join. And it is a generalized join operation, sometimes also called a condition join, where instead of, so you can have an equality join, or you can have an inequality join, or a less than join, or a greater than join, or any predicate that you want. So for a given random join, you can actually specify the join operations that you want to condition it by. Right. So that is in general what we call a theta join. A theta join is very general. So if you remember, the resultant schema of a natural join removed all the common attribute names and had just one entry for every common attribute name. Uh, a theta join does not include a project operation. So you would need to specify your own project operation on top of that. That is why we say that a theta join is essentially a select operation on your Cartesian product. Null padded results are not allowed in a theta join, unlike an outer join. However, you can actually have a left outer theta join and a left inner theta join, and right outer theta join, sorry, and things like that. Okay. So for example, a theta join would basically have a syntax like this, where we say select star from borrower in a join loan on this particular condition, where borrower.loan ID equals to loan.loan ID. We can do the same thing by just having a comma here and getting a Cartesian product. But this is essentially the generalized version of a theta join, where we have a select star from borrower in a join loan on borrower.loan ID equals loan.loan ID. And we can see that loan number is repeated twice. And we see that we have this natural join across our two tables, borrower and loan. So essentially, our theta join would specify the type of join that we want to do and the condition that we want to make using the on clause. Okay. Um, so we can have table 1 inner join table 2 on a particular condition, and that is your general condition in the from clause for your theta join. Again, if we inner clause is the term inner is optional, so you can choose to remove that and just say table 1 join table 2 on condition this. Essentially that means that duplicate attributes are not removed, but by default it is going to consider things as inner joins. However, we can also specify something to be an outer join, and in that scenario we would like to specifically say if it's an outer join. We can also, since we are joining all those two or more tables together using a particular condition, we can also specify the new attribute names if we want to. So given this new set of joins and this new table that we have, we can also specify the attribute names as relations attribute 1, attribute 2, and so on. This is very similar to a derived relation, right? We are taking multiple relations together and deriving a new relation using a join operation and applying some conditions on that operation or on that relation. We can join multiple tables using theta joins as well. We can say select star from customer as C, and then we have two theta joins. First is join borrower as B on, where customer C equals B dot customer name. So basically joining customer with borrower. And then we can have another theta join that joins loan with the borrower. Right, so join borrower from with customer name, C dot customer name equals to B dot customer name, and join loan with B dot loan number equals to loan